Welcome back. So we have been talking about regression models and how we could use linear algebra to compute model parameters, or rather estimate model parameters, as well as fitted values and residuals. Right? So, so this is what we have been doing. There is a regression model, and we have taken a simple linear regression model. Okay, and so what our aims are several. One is that we estimate model parameters, which is beta naught and beta 1 according to our notations. And then also we compute the fitted values and residuals, which we haven't yet done, but we will do so. So fitted values and residuals, right? And we intend to do both of this using the tools in linear algebra, right? So using the tools of linear algebra. Okay, now if you also recall that in the beginning, in the first lecture, in fact, the very first lecture of the class, I did tell you that in higher dimensions, we take recourse to linear algebra often because it provides some equivalence between the calculus-based tools and geometry-based tools. So typically, if you, based on your training, the kind of courses that you have taken before, I mean, you have seen that we use calculus-based tools to interpret or attempt to visualize geometrical objects, like how points are distributed in space, so on and so forth, right? Okay, and there in that same class, I argued that linear algebra provides a very nice abstraction of the same geometry as long as we are dealing with finite dimensional space. So the only difference between calculus and linear algebra is calculus can also deal with infinite dimensional spaces, which linear algebra tools cannot. Okay, all right. So I mean, but mostly as far as most of the advanced computing techniques are concerned, including primarily machine learning and inferencing, right? We do not try to inference over infinite dimensional spaces because in real life situations, we really don't know what that means, right? So linear algebra serves our purpose just right. I mean, we really don't need to worry about infinite dimensional spaces, okay? But since there is some equivalence between the tools in linear algebra and calculus, at least over finite dimensional spaces, I mean, it's worth spending a little time in trying to establish that connection a little bit more before we proceed towards computing the fitted values and residuals. Okay, all right, and that we will do by taking a real life example that I already have given you last time, which is try to figure out if we can fit a regression model between disk input output devices and the CPU type. All right. Okay, you have already seen the model. I mean, we really don't know how good that model is. I mean, we haven't really evaluated the goodness of fit parameters. We will do so in today's class as well. But so if you recall, I mean, so we have to recall a couple of things. If you recall that, our model, if you recall that our model is this, correct? Right, okay, and a typical training example is an ordered set of points, right? Okay, and we have such multiple ordered set of points so that we could have an overdetermined or an underdetermined system of equations, and the abstraction, and so there is some error also. There is some error which is normally distributed with zero mean and standard variance, right? And an abstraction of this model and an abstraction of this model is nothing but, beta naught, sorry, actually, beta x plus epsilon, right? Just to be sure, these are all in vector notation, right? Okay, where y is an n by 1 vector and beta is n by 2, and this is 2 by beta is 2 by 1, sorry, and so this will be actually x beta, right? X is n by 2 and beta is 2 by 1, right? And epsilon is once again, the error is once again n by 1, right? Okay, so if we do this abstraction, what we also came to know are the following, is that the model parameters that we estimated, the model parameters, I'm not going to repeat the calculation, the model parameters, estimated model parameters are beta naught and beta 1, and those are simply these two, right? Which is y bar minus x bar y bar over minus okay, this is your beta 1 and beta naught is nothing but okay. All right. So these are the model parameters that we estimated via the tools of linear algebra, which is matrix inversion and all that, and there is the pseudo matrix involved in the computation, if you recall, right? Okay. You should also recall that there was this matrix, and this will be handy. There was this matrix which was this, right? X transpose X inverse X transpose Y, because this is really what you have to do in order to find out what your beta naughts and beta ones are, and that has some form, right? I mean, we really don't, we just don't, no need to write this, okay? All right. So, but now, as I said, we will just go back a little. We'll just go back a little, and we'll see how from the data using the calculus-based approaches, we actually arrive at the same estimate. Okay. All right. So let's look at this example again. All right. And this is what these model parameters are according to a calculus-based estimation. All right. Now, if you look at this carefully, you will see that the estimated coefficients beta 1 particularly, even though it looks like it is different from the one which we have already computed, it's actually not, because if you divide the numerator and the denominator both by n, right, which is the number of samples, you actually get back the first term which we have already derived, which is x bar xy bar, and then this is x bar y bar, and then this becomes x bar square, and then this becomes, I mean, x bar of x square of bar, right? So just divide this by n, and you are going to get back to what you have already obtained, right? I mean, this particular beta one. Okay, there is no inconsistency between the beta naughts and the b naughts, so we will just leave it there. All right, and you know what each one of these guys stand for, right? X bar is the average observations, average of all observations. Y bar is the average of all predicted values, right? And summation of xy means this, and summation of x square also means this. Okay, all right. Now, and this is the particular example you have already seen, that fitted model, and the model also from an explainability point of view makes sense, right? Okay. However, we really do not know whether the coefficient values that we obtain here are significant or not. We will see that in a bit. Having said that, let's just go to the derivation of the regression parameters, which is the model estimation, right? So we know typically that the error at each observation, right? Error at the ith observation is nothing but the difference between the actual value and the fitted value, right? Okay, and this fitted value comes from your regression model. Okay, you can read this off either as beta naught plus beta 1 xi or just b naught plus b1 xi. Okay, and so for a sample of n observations, your average error has to be this. Okay, all right. And the assumption is you set the average error to 0 because that's what you want to achieve, right? You set the average error is 0. Okay, and so if you do that, you have an expression for beta naught, right? Or b naught. So you substitute that in that particular expression for error at an ith observation. Okay, and therefore what you obtain is something like this. It's a very, very simple algebra. I mean, if you can work this out yourself, right? I mean, you replace that, you know, beta naught, right? Basically, you replace this beta naught in this expression, correct? Okay. So I think, I don't know if I can point this out, but anyway. Therefore, you have this simple enough expression for error at the ith observation. Now, remember what your goal is. Your goal is to reduce the mean square error, the square of the errors, to a minimum, right? So you got to compute the sum of the squared errors. So this is your sum of the squared errors. Now, recall that your error at ith observation is this. So sum of the squared errors will be a square of this entire thing. So there will be a square of this term, the square of the second term, and then the a minus b whole square formula, right? Which you apply. So if you do this correctly, what will happen is that you should be able to simplify this, right? And this is very, very simple. This is the sample of observation. So this is the variance of the, all the predicted values, right? So this is simply the variance of y. This is nothing but the variance of x and y jointly, correct? And the last term is nothing but the variance of x values, right? Okay. So what will happen is the following, is that, since the summation is from I is equal to 1 to n, you have precisely n minus 1 such observations. So the denominator and the numerator cancels out from both the second term as well as the third term. And you have a nice compact expression like this. Okay, we have gotten similar stuff when we did the linear algebra techniques, right? So this is the one that we are supposed to minimize, right? Now, if you take a calculus approach, I mean, if I may ask a question at this point of time, how are we going to minimize this? If you want to take a calculus approach? How are you going to how are we going to minimize the sum of the squared errors by using calculus-based tool? Sharbari?
Differentiating and finding the minima.
Right. Differentiating with respect to what?
Differentiating with both beta 1 and beta 2. Beta naught and beta 1.
Correct. Very good. So we do that. We do that in the next slide, right? And if you do that, I mean, from the expression itself, you can see if you do that, because the first term is actually, a sum of some constant value, right? These numbers are known. So this is sort of invariant with respect to your parameters. So if you differentiate with respect to beta 1 or b1 first, this is what you are going to get, correct? And you set this equal to 0. Simply you set this equal to 0 and solve for b1, you are going to get this. Okay, all right, that's exactly what you are going to get. Okay, now you divide this by n, you divide this by n throughout, and you are going to get back this to this expression. If you divide this by n, this is what you are going to get, right? This beta 1 is what you are going to get. Okay, so similarly, I mean, I can find out the values of, and then see, all you need is beta 1, right? Or b1. Once you know b1, I mean, how are you going to figure out B naught, because B naught is just y bar minus B1 times x bar. So plug in the expression for B1 and simplify, and you are going to obtain the value of B naught. Okay, all right, okay. So the allocation of variation is once again another important tool that just tells us that what is your error variance without regression. So this is purely the variance of the response variable, which means that, I mean, whatever you observe and whatever you predicted, you take the difference of it, right? So then we compute the variance of errors without regression. And this is nothing but, turns out if you do that, it is nothing but the variance of the y values, okay? So therefore, the sum of the squared errors without regression would also be the variance of the y value. And this is known as the total sum of the squares, or SST. Okay. So it turns out that a very simple calculation will tell us that the sum of the squared, the total sum of the squared, is nothing but the sum of the squares of y, right? And the sum of the squares of y bar. Okay. All right. And difference between the two. So in general, if you flip around, if you move around the signs, I mean, you can easily see that your total sum of the squared errors is nothing but the sum of the squared errors due to regression, and sum of the squared errors explained is the sum of the squared explained by the regression, right? And from this, the fraction of the variance that is explained by the regression determines how good your model is. And this fraction is often called as the coefficient of determination, or R square. So for simple linear regression models, for both simple linear regression models and multiple linear regression models, this R square is a very, very good measure of the fit. But with a caveat, there is a caveat, okay? And I'm going to tell you that. So what is R square? R square is nothing but the ratio of sum of the squared due to regression divided by the total sum of the squared errors. So needless to say, what you can see is that the value of R squared will be restricted between 0 and 1, because SST, the denominator, is greater than SSR, correct? Okay. Now, so basically the conjecture is the following, and there is, I mean, you have to really take this conjecture with a pinch of salt, is that the conjecture says that the higher the value of R squared, the better is the regression, okay? And so if R square equal to 1, you have a perfect fit. If R square is equal to 0, it's a really bad fit, right? And we also use the sample correlation to determine all of this, right? So from the example data of the disk input output devices and the CPU time, we can actually compute all of these values. So you have to find out SSE, you have to find out the SST, and if you know both SSE and SST, using those values, you can compute SSR. And then you use the formula of R square here, okay, you see that the R square value is pretty good, which is close to 1. It also says that the regression model that you have come up with, which is the equation of a line, explains 97% of CPU times variation with respect to the disk input output device. It sounds pretty good, right? But I mean, again, I'm saying that we have to be really, really careful before making a statement like this, okay? Now, there is a standard deviation of errors with degrees of freedom. I am going to skip all of that, right? But for the same example, I mean, I just have these numbers that could be easily computed, just simple algebra. What is very, very important is the following, is that when you are measuring, when you are estimating the model parameters, which are beta naught and beta 1, or B naught or B1, whichever way you look at it, right? I mean, how good are those estimates? I mean, with what confidence can I say that those estimates are good enough? In other words, before making a statement on my regression model purely based on the value of R square, can I check the values that we obtain for beta naught and beta 1 from the empirical example, whether these values, what is the confidence interval of these values? Guys, please understand, I mean, the current regime of deep learning research completely ignores this. So when you are predicting a sample, right, as positive or negative, considering a binary classification problem, we just prefer to report absolute parameters or metrics of classification, which means that, well, We just say my, you know, accuracy is 98%, my sensitivity and specificity values are this is my AUC, blah, blah, blah. We do not take into account the fact that there could be label noise. And because of that, the particular accuracy metric that you are reporting, you are not reporting the confidence interval. How much confident you are that the particular sample belongs to class A or class B. Okay, all right. So which is why you see deep learning algorithms make confident wrong predictions. They make these predictions confidently. Okay, all right. And unfortunately, there are really few people who are bothered about it. But nonetheless, that's just a different, that's a context that I wanted to give you. All right. So assuming that we are able to compute all of this, right? Also at this point of time, I would like to give you another example, and just to impress upon the fact that why the R square value should not be blindly tested. So this is, let's say, R square value. Okay. So I'm just saying that, let's say my R square value is 0.998 for a particular data set. Just saying, okay, for a particular data set. And what exactly is this data set? I'm going to tell you. The predictor variable is equilibrium temperature. The predictor variable is equilibrium temperature, and the response variable is surface temperature. Okay, all right. And you have a simple model which says that it is beta naught plus beta 1x plus some. Okay, so this x is your equilibrium temperature and y is your surface temperature. And given a particular data set, and I have a really large data set, about 4,500 data points, I have found out the value of R square is really good, which is this 0.99. So my question is the following. Is this a good model? What do you think?
So what is X? Can you repeat again?
Okay, the question is that X is equilibrium temperature, the predictor variable. Y is surface temperature, which is the response variable. Okay, I give you a data set of 4,500 data points. Okay, I am also telling you that there is no doubt about the quality of data. The data is good. Okay, all right. And this is the R square value that I have computed from my linear regression model, which is 0.998. What I'm going to ask you, what I ask you is the following: is this a good model? What do you think? I mean, obviously, I know you are confused, right? Because you think that I have asked a question, I'm asking if this is a good model, right? If the answer is so obvious, I wouldn't really ask it, correct? I mean, which is, I mean, you are right, okay? Because from the number, from the statistic itself, it appears that it's an excellent fit. So what am I missing? You should, I mean, in order to answer this question, you should really think the one example that I gave you in the last class, and I have, referred to that same example again in today's class, and look at the predictor variable and the response variable before you answer this question.
So, isn't the surface temperature going to be equal to the equilibrium temperature anyway? I mean,
No. For planets with rocky surfaces, but I think you are on the right track. I mean, you are thinking on the right track. But generally speaking, from an astrophysics point of view, for rocky planets, there is a strong correlation between surface temperature and equilibrium temperature. Okay, but for
okay.
planets which do not have rocky surfaces, such correlation is absent. I mean, we really don't know. I am asking this question because this is a published paper in a very good journal. It is really top journal, really top astrophysics journal. And there they have shown that they have fitted a regression model. And their claim is the following: for planets where we cannot compute the surface temperature, this is the formula that we should be using to estimate the surface temperature. That was their claim. So just to give you a little more context, for planets with rocky surfaces, we don't need to estimate the surface temperature, we can measure the surface temperature. For planets which do not have rocky surfaces, we cannot measure the surface temperature, we have to estimate. So it was an important problem to study. It was an important problem to study nonetheless, but is the approach correct?
So, as you said that for planets with non-rocky surfaces, like this does not really hold. You said that, right? It's not correlated in this way.
No. Why wouldn't it hold? That's the whole question. Because the paper claims that this model holds. And they went ahead and plugged in the equilibrium temperature values for several non-rocky planets and estimated the surface temperature, and they are reporting that surface temperature as the estimated surface temperature of those non-rocky planets. Right? That is their claim.
But then, if they're not able to measure it, then how are they so sure that this estimation is right? I mean,
My question is more from a model perspective. I mean, forget what they are thinking, or forget what the physics says. This is not a physics question actually. That is why I gave you a hint. Right? What was the example that I gave you? The example that I gave you for regression is that the predictor variable was disk input output devices and the response variable was CPU time. So what are the nature of those predictor and response variables? And that should give you a clue about how to answer this question. What are the units of the predictor and the response variables in the example that I gave before? That's easy, right? I mean, the disk input output devices is actually dimensionless, right? I mean, it could be 1, 2, 3, 4, 5, right? Based on what kind of disk input device output devices you have. And your response variable is CPU time, which could be in microseconds, milliseconds, nanoseconds, right? Right? So yeah, go ahead.
Oh, so like in that case, the nature of the two variables is different.
How different?
Um, like, I mean, CPU time is time. Like they have different units, so their natures would be different. That's what I meant. But then, sir, here these two are temperatures only. So, like, how can we draw an
Right,
analogy?
exactly, exactly. So, I mean, as I said, see, if both the predictor and the response variables come from the same set of observations. So, in this particular case, what happens is, I mean, the both are in the units of both of these variables are in either in centigrade or in Kelvin, right? Okay. So, the scale of measurement is the same. In a regression model, you have to remember this, that your response variable and predictor variables should originate from different observation sets. So when your response variable is something like CPU time, your predictor variable is something like disk input output devices, right? Okay. And you could add another variable, let's say memory devices, right? So those are different. They have to be different. That is how you establish a sort of a causal relationship between the X and the Y. Okay. In this particular case, you should not be even attempting to do this. So the basic premise of the model is itself wrong. This is not a statistical problem to begin with. To figure out a relationship between equilibrium temperature and surface temperature is a simple algebraic relationship will exist, right? And one is actually the derivative of the other. We know that from physics. But from a modeling perspective, from a statistics perspective, since both of these variables come from the same set of observations, it makes absolutely no sense to treat a regression model. This is not a statistical problem at all. Okay. In fact, I was one of the referees of the paper, and there would be another other referees, I'm sure. I rejected this paper thoroughly in the first, second, and third iterations. But I think the editor thought otherwise, and he made the paper through. Okay, and now there is severe criticism of that paper in public domain. Okay, so be careful. So whenever you are regressing, keep this in mind that your y and x have to come from different set of observations. Okay, all right, and
So
yes,
why is it actually needed for them to be of different?
because otherwise it's not a statistical problem, right? I mean, a statistical correlation, when you are trying to measure statistical correlation, if you know that the correlation is already obvious because both are the different forms of the same variable, like both are temperatures in this case, right? Equilibrium temperature and surface temperature. Both are different forms of the same variable, right? So there is, I mean, if you look at the solid planets or the planets with solid surfaces, I mean, you just plug in the equilibrium temperature, then there is a simple correlation that exists between the two. So you don't need a regression model, right? So therefore, this is not a statistical problem at all. You said so when you regress, you should be regressing between length and weight, right? So not length, the height and weight. So height and weight of individuals, right? I mean performance of individuals based on their educational background, right? So these are sort of problems that are regression problems because they are not really, there is no apparent correlation that already exists. If an apparent correlation exists and it is already known a priori, there is no point of doing a regression model. Regression is trying to figure out things that are not known to you.
Right, sir. Okay, understood. So just to clarify,
Okay.
so what you're saying is key we already know the relation between them beforehand, so it doesn't make sense to do a regression. But even if we do a regression, it is quite likely we'll miss the one that we already know, right? Isn't it
Yes,
possible?
yes, right. But the whole point is, it is not only important. See, why do we do regression? We do regression to figure out unexplained or unknown relationships between two different set of variables, right? So when you are doing this, when you are extrapolating this for planets which do not have solid surfaces, this relationship does not hold, cannot hold, right? So if you want to extrapolate this model to non-solid surfaces by simply relying on the fact that your R squared is 0.998, then you are actually making a wrong inference altogether. Okay, so that's where the objection lies. All right.
Okay. Yes.
But generally speaking, always know this, that whenever there is a y and an x, they have to come from two different sets of observations. There has to be no apparent correlation between the two. Okay, and the best way to check that is that whether the two sets of variables have different measurement units. Okay, all right. So having said that, let me just move back to the PDF slide, right? And let's now look at, so when you have a model, your beta naught and beta 1, what I wanted to say is that this has to have some confidence. Okay, some confidence interval. And I think most of you have taken a basic statistics course, so you are familiar with 90% confidence, 95% confidence, 99% confidence, so on and so forth, right? Okay. So precisely the question that I'm asking is that if I say my beta naught, so let me go to this example. I'll have to go back and show you the model that, oh, not this, I'm sorry. So let me go back. If you recall the model itself, right? Where is the model? Yeah, so this is the model. So your model says that your y is equal to beta naught plus beta 1x. And so the values of beta naught or beta 1 are minus 0.0083 and 0.2438 respectively. Okay, so the question is, with what confidence can you say that these values are true? Okay, all right. And this is simply done from statistical tables that are typically at the end of your, basic statistics textbook, right? Where you look at the t values or f values, right? And use those t values and f values to determine your degree of confidence. So what happens is the following, is that you have to know these guys, SB0 and SB1, which is computed coefficients, which are both estimates of beta naught and beta 1. So these are just formulas, right? And then you use this kind of a confidence interval. So what really happens, it also depends on your degrees of freedom. Your degrees of freedom are nothing but, if you know the number of data points that you have, so this is what you have. So let's say you are assuming that the data points are, having a t distribution, then this t1 minus alpha by 2 comma n minus 2. So this is nothing but the 1 minus alpha by 2 quantile of a t variate with n minus 2 degrees of freedom. So let's say your alpha is just your alpha could be 0.1, let's say. So if your alpha is 0.1, then you just plug this in, right? You plug this in, so it's 1 minus 0.1, which is 0.9 times 100, which is 90%. So a significance level, for a significance level of 0.1, your confidence intervals are 90%. So if you are measuring the values of beta naught and beta 1 with an alpha is equal to 0.1, then you are saying essentially is that with 90% confidence, I can say that this beta naught and beta 1 values are significant. Okay, all right. So, and then I use this simple formula. And so these values of SB1 and SB0 come from the t distribution for that corresponding t value. So when you plug in alpha is equal to 0.1, this is 1 minus 0.1 by 2, which is 0.95, right? And this is n minus 2. Let's say in this particular case, you have 7 data points, if you recall. So this is 7 minus 2, 5, right? So you look at that particular intersection of the row and the column in your statistics table, and you just pick that value. Okay, and that is your t value that you will plug in. So if you plug in that, right, for the particular data, right, this is what you get. You get, I'm using a 95% confidence interval, so that means my alpha value would be 0.01, which is fine, right? So this is what I'm getting. So this is for 90% confidence interval for beta naught and 90% confidence interval for beta 1. So let's look at this value of beta naught carefully. And this will always give us a range of values because of the minus and plus, right? So my 90% confidence interval for beta naught is this. Okay, all right. Now, do you think this is something that we can trust. So these are all probabilistic measures, guys, right? Now, if your values of beta naught oscillate between a negative value and positive value, what it also implies that there is a possibility that your beta naught could actually cross the x-axis, isn't it? Now, whenever it crosses the x-axis, your beta naught value becomes 0. So there is a probability that your estimated coefficient beta naught could be 0 with a 90% confidence, right? And that is not acceptable. On the contrary, look at the 90% confidence interval for beta 1. The 90% confidence interval for beta 1 is from 0.2061 to 0.2814, which means there is not even a tiniest probability that with 90% confidence you can say that beta 1 crosses the x-axis. Okay, so this is significantly different from 0 at this confidence level, and that is why we can say that this beta 1 value, whatever beta 1 value that we got, whatever value, okay, this beta 1 value is significant. But we cannot say the same thing about that beta naught value. So the point I'm trying to make is that in a regression model, do not just look at the value of the coefficient of determination R squared to come to a conclusion about the goodness of fit of that model. This is a mistake that a lot of, I don't think textbooks make this mistake, but people also read from Wikipedia and a lot of blogs on Medium and blah blah blah. I mean, most of the time these things are missed. Okay, all right. So therefore, I mean, we cannot say with 90% confidence that the computed value, the estimated value of beta naught and beta 1 both are actually trustworthy. So whenever that happens, I have to reduce my confidence interval or my confidence level. So if this is not working at 90% confidence, I can compute the 80% confidence, which means I have to change the value of alpha, right? And that is possible. Okay, all right. So for every regression model that you would ever practice in life beyond bit planning, all right, keep this in mind that for all those coefficients that you estimate have to have some confidence interval. Okay, all right. So I mean, so this is it, right? Okay. So let me. So this is a simple linear regression model. What I also wanted to show you is, so there are other case studies as well. I mean, so let me. So there could be better confidence intervals if you have more data or something like that, right? Okay, but I mean, let's not get into that. What I wanted to tell you is something else. Okay. Now, a simple linear regression model, the reason I'm saying this is that the slightly more extended version of a simple linear regression model where you have more than one predictor variable, right, also follows the same linear algebraic abstraction. Okay, so like this particular example. So let's say you have a bunch of predictor variables, right? Okay, so let's say your CPU time no longer, you are not interested in investigating the CPU time with respect to input output devices only, but there are a bunch of other predictor variables that you wish to throw in, right? So, and you have a sample of n observations, and clearly what you can see is the following, is that you can write each observation, each data point in the following manner, correct? Okay, all right. And clearly what you can see is that the same system of equations can be abstracted using the linear algebra notation. Nothing changes, okay, all right. But as usual, as in the previous case, your x vector is, I mean, your x matrix is not a square matrix. So what you have to do is you have to sort of resort to the same pseudo inverse kind of a thing, which is exactly what you do, right? So we have a new data set where we are investigating the correlation between the CPU time and the disk input outputs and memory size. Okay, once again, please note that this memory size is once again is obtained for or collected from a set of observations which is significantly different from this input output and also CPU time. Okay. Now there are more complex questions that need to be asked. I mean, I will not get into the statistical details of it, but whenever you are throwing another variable, additional variable into your model, the first thing that you should be checking is that whatever you are throwing in extra is not already represented by what is existing in the model itself. In other words, is there a strong linear correlation between the disk input device, output devices and memory size? If the answer to that question is yes, then there is no point in throwing in memory size as another predictor variable. Okay, it will actually make a very bad regression model. Okay, so in order to solve this problem, you have to compute the x transpose x because you have to make the matrix square. Because if you recall, your pseudo inverse is x transpose x inverse times x transpose y. Correct? Okay. So you compute this, you compute blah blah blah. All of this is routine, right? Okay. And you arrive at a new model. Okay. Now, I mean, forget the statistics. Just look at the interpretability part of the model. So what does your model say? Your model is saying that my CPU time is equal to some constant value, right? Okay, plus some coefficient, which is the beta naught, right? I mean, not beta naught, sorry, this is beta 1 times the number of disk input output devices, and beta 2, which is the new coefficient that you have to estimate because we have thrown in another predictor variable times memory size. Please look at this model carefully. Okay, and tell me what you think. Just look at these numbers, 0.1182 and 0.0265. And tell me if this is if this improvement or this extension or this augmentation of a model was really required. That is my question. Did I really require throwing in memory size as an additional predictor variable? So let me open up my calculator. Okay, so this is what, 0.1182 divided by 0.0265. Do you see my screen? Do you see my calculator?
Yes, sir.
Okay. So what do you see? You see a number, right? It's about 4.45. Did I do it correctly? Yes, I did. Yeah. So you see a number which is 4.45, right? What do you make sense of this number? And how do you interpret this number?
So are you trying to imply correlation?
I'm not trying to imply anything. I have asked a question, right? What do you make sense of that number? How do you make sense of that number 4.45? Purely from an interpretability point of view of the model. Doesn't it mean that the effect of the disk input output devices on CPU time is 4.45 times larger than the effect of memory size on CPU time? Right? Because what does this coefficient value represent? Like, for example, okay, So forget about this example. Let me go back to the simple linear regression example. I just, is that, yeah, we'll go back. Go back to the model. Where is it? Where is the model? One that is fine. Here is the model. How would you interpret this model? So here you have two coefficients, right? Your coefficients are beta naught and beta 1 only. Okay. So your beta naught value, the significantly smaller, is significantly smaller than your beta 1 value, correct? Which means what? The real effect of the predictor variable, which is the disk input output devices, on the CPU time is much more pronounced compared to the situation when you don't have it. So I mean, if I take away the disk input output devices from the model, I mean, you have a CPU time which is insignificant, right? And that is how you should interpret this model, right? When there is nothing going on in your system, what is your CPU doing? Almost nothing, right? Okay. So, and how do you know that? You know that by computing the ratio between this 0.0083 and 0.2438, which is between beta naught and beta 1. So that is actually explains your relative effect of one variable on the output variable compared to the other, right? Okay. So I extend the same logic. To a multiple linear regression model where now you have two predictor variables x1 and x2 and an extra coefficient. So based on the comparison of these coefficient values, you can say that the effect of the disk input output devices on the CPU time is much more pronounced than the effect of memory size. Okay. Now, why it happens? Maybe because the disk input output devices and memory size are strongly correlated. Okay. All right. So therefore, I mean, if you look at the confidence intervals, I think, see, so for the same data, now we are computing the 90% confidence interval of all the three coefficients that we estimated. So the 90% confidence interval for beta 1, beta naught is between minus to a plus. The 90% confidence interval for beta 1 is from minus to plus. And the 90% confidence interval for beta 2 is also from minus to plus. Meaning what? With 90% confidence, I cannot say anything about the correctness of the estimated coefficient values. And why is it happening? Was it happening before when I did not have that memory size thrown in as an extra variable? No. So it is very, very likely that why now my model is completely out of sorts. I cannot have a 90% confidence in my model. That is because that I have thrown in an extra variable that is not required. Okay. And if you compute the correlation between, I think it's somewhere over here, if you compute the correlation between this memory input output and the memory size, you will see that the correlation coefficient value is really, really strong. And this is known as the problem of multi-collinearity in regression models. Okay. So if you throw in an extra variable without checking whether that extra variable is already correlated with an existing variable, you are going to encounter this kind of a problem. Your model does not become explainable, not an explainable model. Okay. All right. So these are some of the nuances, because I don't really have the, mandate in this class to talk about more statistical nuances of multicollinearity, but this is one of the problems of multicollinearity, which is why estimating confidence intervals is so very, very important. Okay. I don't know how many of you have taken that applied statistics course, right? I have no idea, but you should really take it in order to understand this better. Okay. Okay. So now, so therefore, I mean, what I wanted to impress upon you is that I'll just write in here as summary, is that it's important to have confidence interval for estimated coefficients. It's really, really important, right? Okay, that's number one. Also check correlation between predictor variables. Okay, and all that you are able to do is because of a synergy of technical equivalence between linear algebra and calculus-based tools. Okay, all right. If you had to do it by hand and if you had to do it by a lot of bookkeeping, you wouldn't have the luxury of actually looking at the nuances of this kind of models, and the development of machine learning in general and statistical inference would have been pushed back by another 200 years. And that is why these tools are kind of important. Okay, all right. So what we are going to do in the next class is the following, that we will focus our energy on computing the fitted values and residuals using the same linear algebra techniques that we have seen in the last class. Okay, and then I'll come back to the data and figure out whether these residuals make sense or not. And in the process of doing so, we will explore some properties of matrices. Okay, so this will be the essence of our next lecture. Before I wrap it up, I realized that, and it's really strange with Google Classroom, I thought that you guys had your test 2 grades immediately after you wrote the test, right? Apparently that's not the case, but your grades have been ready for a long time. So please email the TA Pavan if you want to know your test 2 grades. Okay, and I'm sorry about this confusion. All right, I'll see you in next class.